It's a great privilege to have been awarded the King Faisal Prize, and I will, in the interest of what I assume is an attenuated talk, give as much of this as I can. I apologize for anyone who was here yesterday and heard this talk. I'll try to make it a little different and emphasize other points. I do have limited disclosure. I've not received any investment in any product that I've tested in clinical trial. What I want to do today is to build the story of how we got to where we are and how that makes a difference. And in starting that story, I want to just emphasize about corticosteroids. This has become the standard of care, and we did a study back in 1989. It was distinct for many reasons. There were 4 of us who had been at NIH and developed a program called the Clinical Investigation of Duchenne Dystrophy, and we did some of the early natural history studies of the disease, but more importantly, we did what was very unprecedented at the time. We did a 100-patient study in Duchenne dystrophy using prednisone, and we're able to show, as you can see on the graph there, that the top line is the prednisone dose, and it improved patients for a period of time, and then before they started a slow decline. That's important because you'll see, and the reason I bring this up is because we use this in clinical trial, and knowing that the first initial dosing of corticosteroids improves patients, that has to be accounted for in clinical trials. And this was, again, unprecedented because it was a dose escalation study, and it now has become the standard of care for this disease. And in that sense, of course, I take pride in that because it was the early development, and then was used now the one thing I wanted to point out was an early study that was highly criticized, and then since then 59 studies have confirmed the results, most of them claiming that they were the originator and did the study initially to show efficacy. I'm not going to say much about the other steroids because of time, but I wanted to point out that steroids have gone through evolution, and deflazacort is one of the changes that took place. It's a commercial product. It has about the same efficacy, and the most recent one is vamorolone, which it has qualities that make it perhaps of more interest, but we don't really know its full potential on the clinical level. And that's where I'll leave steroids to go on to the gene therapy program. I'd like to add that between the time we did the steroid study, we did multiple other studies that have great impact. One of the impactful studies was newborn screening for Duchenne muscular dystrophy, and my happiest moment of the day, at least, was to find out that newborn screening had been approved in Ohio for Duchenne muscular dystrophy. The implication of that will be fully realized once we have full approval for Duchenne dystrophy, microdystrophin treatment, because we'll be able to treat babies at a very early age before the disease can fully manifest. So let's start out. One of the things when I first got into this field, people were dissuaded from doing gene therapy because of the early death of Jesse Gelsinger that I'll come to in a minute. But it was people in science. There was an article in Science magazine that said that gene therapy was over-embellished as a potential treatment, and that the gene delivery and expression would probably be short-lived because the promoter would shut off. that there would be severe liver toxicity from gene delivery. When you push the gene infuse the gene, it would all go to the liver, and the toxicity would be more than we could manifest at a clinical level. And I'll point out that this is predominantly a clinical group, I think, and the importance of your clinical contributions are that managing diseases like that are, with your clinical background, or managing toxicity with your clinical background is very important. The other thing was insertional mutagenesis, that I'll talk about in a minute, and viral capsid immunity. These are important steps that took place as we moved toward actual gene delivery. An important point is about the choice of virus for gene delivery and how we got to where we are today with adeno-associated virus. There were 3 viruses that were competing for gene transfer to serve as the vehicle. The virus serves as a vehicle. The virus has all of its genes removed. The gene of interest is put in the virus, and then it's used for transduction. You rely on the virus for getting to the target cell and delivering your gene. Adenovirus was very attractive at the time. I had an IND for adenovirus. We were about to launch the adenovirus trial. We could put the whole gene, the 14 kb gene, into adenovirus. And right about that time, there was a tragedy that occurred in the field, and that was the loss of a life from a gene transfer for ornithine transcarbamylase. And this is a name that's known throughout the gene therapy world, the death of Jesse Gelsinger in 1999. That occurred within 4 days of the gene transfer. And we see that now, but at that time it was astounding, and the FDA made a huge issue about it and said, you can't use adenovirus anymore. And the IND that I had for doing the experiment was then negated completely. And we had to move to another virus that I'll come to in a minute. But the other one that was attractive at the time was using retrovirus. The reason that adeno and retrovirus were attractive is that they could serve as a vehicle for the entire Duchenne gene. They could house a package 14 kb. Unfortunately, what happened with retrovirus, the condition called insertional mutagenesis. Retroviruses take the vehicle, insert it into the genome, and at that insertional site, if there's another gene that can potentially be disrupted, and that happened in this case, where 5 of 20 patients who were being treated for X-linked severe combined immunodeficiency disease developed T-cell leukemia, and 2 died because of activation of something called the LMO2 gene. And so that kind of tells the story of 2 viruses that were taken out of the picture. And here comes along a small virus, 200 times smaller than adenovirus, which is its major limitation. It's called adeno-associated virus, an unfortunate name because it uses adenovirus as a helper virus for gene proliferation, and it's a single-stranded DNA virus. And what does that mean? That means that in order for a gene to express, once you put it in the cell, it has to be transcribed to a double-stranded DNA, and that double-stranded DNA is where the gene expression comes in. There have been now mechanisms of using adenovirus as a double-stranded DNA to then remove all the previous steps in getting from single to double-stranded DNA. The other point about adeno-associated, which made it attractive, it had no human disease associated, no naturally occurring, and there were multiple serotypes. Why we used AAV9 and RH74 I'll come to in a few minutes, but the strength was that it didn't integrate. Now that has advantages and disadvantages. By non-integrating, that means that the virus is delivered to the nucleus, but not into the genome. And into the nucleus, it has to set up this double-stranded DNA, and in that double-stranded DNA, it acts as an independent chromosome and can express the gene that's attached to it. And the other thing that came up yesterday reminded me to emphasize that this means that there is no, once you deliver the virus, there is, it's not, it can't be passed on by any of the X or Y chromosome. When the cell, if you use it in a cell dividing like the X and Y chromosome do in terms of developing sperm and eggs, the genome that the cytoplasm is lost, and the genome no longer carries the gene of delivery. So it's non-integrating, and that is both a strength and a weakness. And also it means that what you want to do in gene therapy is to deliver the virus to a non-proliferating cell. Muscle and nerve were ideal targets because neither of them turn over. Neither of them divide once you have the established number of muscle cells in infancy, or nerve cells in infancy. So once you put the gene in there, if that cell doesn't divide ever again, that genome the genome you deliver will be permanent to those cells. Makes it very, very attractive for muscle and nerve gene therapy. The weaknesses are mainly in limiting packaging capacity. It only can package 5 kb. If you have a gene that's the best example of 14 kb, like the Duchenne gene, it won't fit in AAV, adeno-associated virus. So we'll see what you do in subsequent slides. And this picture shows the relative size of adeno-associated compared to retrovirus and adenovirus. So the next thing we learned as we moved through clinical trials, these are stepwise learning experiences. They're not necessarily in sequences as I'm presenting, but I wanted to illustrate how we use this information now in our clinical trials now. And one is the supposed low immunogenicity of AAV, which was basically a myth. It is very highly immunogenic, just like every other virus, and so it creates problems. And the first time we learned that was in a gene therapy study we did in limb-girdle dystrophy. This is one of the early clinical trials. And this is before we got to do systemic gene therapy, and doing these limited AAV gene therapy trials in limb-girdle patients. Why limb-girdle is that it's a muscular dystrophy, which is where we wanted to go, but it has genes that are 2 kb rather than 14 kb. So these 2 kb genes will fit in AAV. And so this is an example of one of the early clinical trials. On top you see what we call the transgene with its promoter. It has a muscle-specific promoter, which means that we can deliver it to the muscle, it will be in the nuclear, it won't be inserted into the genome. It'll stay there as long as the cell doesn't divide, and it has a promoter that allows it only to express in muscle. If we inject it, it can go all over the many different organs, but it won't be expressed in any of those organs, so it can avoid toxicity. And in this trial, we started in 1999, but were interrupted by the death of Jesse Gelsinger, and we reinitiated that trial in 2006. And I just have an example of a limb-girdle patient over on the right-hand side of that. It's a little bit milder disease than Duchenne dystrophy, but has many of overlapping qualities. And we had to, in those days, inject the gene locally because we had no ability to make enough virus to deliver systemically. And that is an example of injecting into a foot muscle, the extensor digitorum brevis, with monitoring with ultrasound. You can see the needle going in where the arrow is in the lower panel, and that's what the extensor digitorum brevis muscle. When I took that to the FDA, I said that you're afraid of Jesse Gelsinger, and so am I, but if we can inject this muscle, then if there's any toxicity, we can remove the entire muscle and avoid any serious side effects. But we can also make advances and learn something about whether we have toxicity or gene expression. And guess what? We had both. We had we did 6 patients in this clinical trial. 5 of them were like the left panel you see there that has excellent gene expression with muscle fibers stained with in their sarcolemma where alpha-sarcoglycan is. And on the right side you see that there is no staining. Well, my first reaction was that the technician made a mistake and put the wrong muscle in the cryostat, and there was something wrong. But what we later learned was that this was a patient, it was the first patient that demonstrated for future clinical trials that we had pre-existing immunity. When we looked at, we saved the serum on these patients, and when we look back, we had pre-existing immunity with T cells in that high bar at day 2, which showed that there were already significant T cells that were already generated on day 2, and that the reason that happened is because the patient had pre-existing antibodies, which means that there was an amnestic response against the virus. And this is how we knew that. We looked at patients 1 through 5, and they had a dilution of antibody at 1 to 50, and patient 6, who didn't express pre-existing, had 1 to 1600 dilution. And by the first week, that 6th patient had a dilution over 100,000 of antibody. And what that essentially means is what's shown there is the antibody bound to the viral capsid and prevented uptake by the muscle fiber. So this actually was important because it established guidelines for future gene therapy, and we use that for SMA. And we've used it for Duchenne as well. And so it was extremely helpful. And one of the things I like to point out in clinical trials, and important, is that no matter how negative the study is, you always learn something, and you really need to do it carefully. And you want to prove to the patients, to an extent, that their time that they spend was definitely worthwhile, and that's true in this case. And we also demonstrated another form of pre-existing immunity, or immunity that was generated in Duchenne dystrophy. This was what we call a mini-dystrophin gene therapy trial, taking the Duchenne gene, minimizing it, and then in this case we injected it into the biceps muscle. And you can see we're monitoring it again with ultrasound, and there I am injecting it in to the biceps muscle. And this was the first report of transgene immunity that was I guess back in 2010, quite a while ago. but it was important, and it was the result of, on the top portion here you see components of the gene, not by exons but by spectrum repeats and hinges, and I won't go through that because of time. But on the bottom is the comparative parts of the transgene now that were minimized, that would fit and parallel the gene that's on the top portion there on the upper panel. And when we injected that gene into a patient who had exon 3 to 17 deletion, and deletions are the most common form of mutation in the Duchenne patients, what we did was we could see that antibodies and T cells were generated by expressing this novel protein into an area of deletion of the patient. And I like to point out then that the message from this study was we did get gene expression, no toxicity, but we did create antibodies now, which again set the stage for later clinical trials. And this slide especially, if you look at the yellow portions there, these are all the exons, the 79 exons of the dystrophin gene, which makes it a huge gene, the largest gene in the human genome, and why kids are endowed with that is a big mystery. But in order to make it fit into AAV, we had to minimize the gene. So exon 17 now matched with exon 59, and 44 exons were then removed. And there were competing companies here. This was one we developed and then later licensed to Sarepta. And then Genethon, Pfizer, and Solid had their own transgenes that were all modifications of what we created at Children's Hospital and then licensed to Sarepta. But when we injected this into 3 to 17 is when we had the first antibody and T cell response. So that's number one. But then this study was confirmed. People generally didn't believe that. They said you don't develop immunity from as a result of transgene expression. But at Sarepta, and this is a little bit of the discussion I was having this morning, when you join a company, you don't always have complete control over everything, but one of the investigators says this was a multi-center study, said, well, he'll go ahead and inject this into a patient who has a 3 to 43 mutation, and you'll see the consequences in a minute. And Genethon did the same thing, and Pfizer did the same thing, and the results, so the yellow parts are the gene that was injected into the red parts where the patients are deleted, and now you have immune responses in all those cases, and now the consequences were severe. Inflammatory myopathy, myocarditis, thrombotic microangiopathy, and fatal outcome. So this has become a tenet for clinical trials. So now we have shown you have pre-existing antibody, you have transgene immunity, and these are lessons to take forward into clinical trial. And now the first big lesson we learned was for SMA, and these aren't necessarily in succession. We did many clinical trials. Actually, we did clinical trials for follistatin, for gentamicin, for other clinical trials, and we did exon skipping by that time. We had actually approval for exon skipping, and that was actually the first molecular therapy that we had translated into human clinical trials and to commercial use. But here's SMA, the story in SMA. And the story of SMA is an interesting and important one because it was so difficult to understand the genetics. There were two paralog genes, SMN, survival motor neuron, in 1 and survival motor neuron gene 2. And Judith Melke just finally unraveled the mystery of this genetic disease. SMN1 was not expressed at all, and SMN2 had a mutation that resulted, it was a missense mutation, so you had partial gene expression, but it was only very minimal, not enough to rescue genes. But if we put the SMN gene now into AAV, we could deliver that and rescue the patient or rescue the neurons if we did it early enough. Rescue meaning that if we could deliver the gene before they were lost, we could do single gene delivery one time, and that's the important thing about gene therapy. It is a one-time treatment. It's not repeated, and that's where it has its advantages over exon skipping or any form of chemo, any form of a medication that's given for the disease. Everything else has multiple administrations. This is single gene delivery. And this is in a disease that's so severe that it's recognized within the 3 months with hypotonia, bulbar weakness, and difficulty breathing with respiratory failure. And these babies, this is a study that was done by Richard Finkel in the Natural History of SMA type 1, and 50% of the patients are gone by 10 months. 92% are gone by 20 months, and all are gone by 2 years. Now, when you have that scenario, one of the things about creating a clinical trial is it's pretty easy. The outcome measures are always argued in these clinical trials. What's the best outcome? Is your outcome valid, or so forth and so on? But life or death is not a question. And what we went to the FDA with is if we could extend life beyond 2 years, that we would have unequivocal efficacy in clinical trial. And they accepted that. I won't go through all of which, the multiple visits that we had with the FDA. They wanted us to do studies in SMA patients type 2, which means that they had onsets after 6 months. Well, after 6 months, if you try to rescue neurons that are gone in the first 6 months, you can do very little for the patient. So we argued vehemently that we do gene therapy in the first 6 months, and we started a clinical trial. We did 3 patients in the first cohort and 12 patients in the second cohort. They all had to have rigidly 2 copies of SMN2 because we wanted this to be phase 1 and prove that we could do gene replacement therapy. And that's an important concept. In fact, it came up again in discussions about what is the kinds of gene therapy. One is gene replacement, and one is gene editing. Gene editing is when you change the genome and you edit the genome in place. That isn't what we're doing here. We're replacing the genome. We're replacing the gene. Gene editing is very powerful, but it has had its obstacles in getting to clinical trial. I have no doubt that it will be successful as we move forward, but for presently, the only study in Duchenne dystrophy resulted in the death of a patient. So that's a little bit on hold. But we did a dose escalation study, which is one of the most beneficial approaches you can do in clinical trial. And we used the highest dose of virus ever given in a clinical trial. And in the interest of time, I won't tell you the whole story there, but part of the story is here. The first patient we ever did had a very marked T-cell response and elevated liver enzymes after the gene delivery. And this was very frightening since we were using such high doses of virus. And I went back to the FDA and I said, let us suppress change the protocol and suppress the gene, suppress the toxicity with liver enzyme, with prednisone, and begin to use prednisone pre-gene delivery to help manage the immune response. And the result of that was very good. If you can see the second 2 patients in the clinical trial, we were able to suppress. The blue line is the liver enzyme elevation, and it was very suppressed. We had varying degrees of immune response, but nothing that reached a toxic level. So these steroids worked extremely well in allowing us to give gene expression. And then we moved that on to another cohort. But before we get to that, You can see here in this line that we used prednisone pre-treatment in all the rest of the patients. And then we had dramatic outcome because all patients, when we're supposed to have 92% that die by 8 months of age, by 20 months of age, that all were survived, and by 2 years, when all were to be gone, we had no deaths, and then that went on to later approval. Actually, approval was amazing in those days because we had approval with just 15 patients from the FDA. The results were so dramatic and life-saving and the safety profile was very good. And this illustrates the safety profile. We would give this very large amount of virus and there would be virtually no reaction from the patient. And the most common side effect was liver enzyme elevation and vomiting that would occur at least in 60 to 70% of the patients by day 3, but very manageable. And when we also looked at where we were in dosing versus clinical manifestations, we learned that if you give the dose very early, and the 2 patients in the upper left-hand corner that are marked in orange, those patients were given gene therapy at 4 and 8 weeks, and they essentially returned to normal. If they had a slightly lower CHOP-INTEND, which was a way of measuring their strength, and we had still very good efficacy, but not quite to the extent of returning patients to normal. And then if we waited past 6 months, unfortunately, with low functional abilities, we got virtually no efficacy. And what can that tell you? That can tell you that we were right from the beginning, and losing all the neurons in the first 6 months was not a very good way to move forward. So that has become now the standard of care. And then the next question, which we often get, is how long will efficacy persist? I mean, just give this gene one time, it's sitting in the nucleoplasm. It's not inserted into the genome. How long is it going to stay there and express? Well, this is one example of outcomes at 7 years. We had now, even within this distribution that I showed you between the ones that were practically normal at when we gave the gene, or varying degrees, we had 2 that were basically normal. We had 2 that then could stand, and all that could sit. And this was 7 years post-gene delivery. And on the right side, you see one of our patients who, cute as a button there, raising her arm up for victory in gene therapy. And then our other patient, I'll show you in a second, who's now 10 years old and has no regression at all of symptoms. This is just examples. On the right, you see 4 months post-gene delivery, we have a patient who can raise his head up, and this is one of the early developmental milestones. You ordinarily see it at 4 to 6 weeks, and another that's dosed, that's holding a bottle independently and having very good arm control. This is one with good body control that you can see here, good trunk control, and dosed at 2 months, and this is 6 months post-gene therapy. And this, of course, is our hero of the study, who was dosed very early, who could now climb a challenging wall. And over here on the bottom, he's the American Ninja Warrior and doing very well. And over on the right is taking his briefcase and going up to see his business associates. So, and that reflects really the disease, and that led to FDA approval just from these first 15 patients. Things have gotten much more challenging at the FDA now, and that is reflected in our Duchenne patients. And if I forget to tell you, we've done over 200 Duchenne patients now on the way to our final phase, which I'll explain in a second. A couple things about Duchenne dystrophy. My stimulus for doing this, I mentioned this in our previous discussion a few minutes ago, was my first patient I saw with Duchenne dystrophy in 1969 when I was at NIH. This is a typical appearance of about a 7-year-old with Duchenne dystrophy, with toe walking, large calves, hyperextension, and patients with Duchenne dystrophy importantly have elevated CK at birth. We've proven that in another study, which is in our newborn screening study. We had all the patients with Duchenne dystrophy and newborn screening are born with CKs over 2,000. So that gives the opportunity for doing gene therapy pre-birth, and really potentially completely reversing the disease. Patients with Duchenne have delayed milestones, loss of ambulation in teenage years, and loss of life at somewhere in late teens or early 20s. The first trial we did, the first vascular delivery systemic gene therapy trial we did was an open label trial with microdystrophin. And by that time I had the IND, and Sarepta wanted to partner with us. And I'll just point out that industry is an important partner because these trials are way beyond what we could afford to do as a small academic center. And we did the dose we used, not unexpectedly, was the same dose we used in our SMA gene therapy trial. We did 5 patients between 4 and 6 years of age, and we excluded exon 3 to 17, not surprising, because we had learned that the gene expresses in there, and don't do that, and we already saw what happened if you did. The other thing we have here is we had good gene expression with AAV9 in SMA, and I didn't emphasize that enough, but that was another, AAV9 was the window of opportunity because AAV9 crosses the blood-brain barrier. But for Duchenne, we decided we would use a virus that had been isolated at Nationwide Children's Hospital by one of my close friends, and we used that virus called AAV-RH74, and that virus then really opened the window for treatment of the Duchenne patients. Why RH74? I just said because it was isolated nationwide. It could distribute to all muscles, heart, and diaphragm, and this was the cassette that we used. Notice now the promoter is not MCK, but MHCK7. We chose that promoter because it could express in both heart and skeletal muscle. And for all the diseases, and that include limb-girdle that we're doing now, for those diseases that express in the heart, we prefer to use this promoter. And this promoter was developed by Jeff Chamberlain and his colleague at Washington, at University of Washington. And the microdystrophin now is slightly different. It has not so much important to emphasize, but this is the model that we used that was an extrapolation from a patient who had Becker dystrophy that lived past 60 years of age. And in using that, it had 4 spectrum repeats, very small compared to 24 spectrum repeats, 3 hinges as opposed to 4, and importantly did not need a C-terminal as part of the gene to express fully. And there we put it in AAV-RH74, monitored the patient carefully, giving again prednisone pre-gene delivery, and these were our first patients. We were very careful about gene administration and using IV perfusion pumps to deliver the gene. And the results were very gratifying. We had very high gene expression. Over 80% of muscle fibers express the dystrophin, microdystrophin. And if you look on the bottom panel in Western blot, it shows full-length dystrophin is absent, but microdystrophin is very robust in its gene expression. And again, this was a very safe trial. We had liver enzyme elevations and nausea and vomiting, but very little else with using RH74, and we had excellent gene expression. This is a child right after we gave the gene delivery and doing extremely well. And here's what he could do at about 6 months, unequivocal chasing, participating in sports and playing with his colleagues. And this one I like because it shows reciprocal stair climbing when Duchenne kids can never do that. And here you see the example of 2 days post-gene delivery. His mom sent me these pictures. Could hardly walk upstairs, no reciprocal stairs. And then 60 days post-gene delivery, he's walking upstairs without any delay. And then as far as how long gene delivery lasts in the Duchenne world, we've found this is 4 years post-gene delivery, and he can stand up without a Gower sign. And if you look at other outcome measures, we have the North Star Ambulatory Assessment, which is a panel of outcome measures. We have time to rise, time to climb stairs, 100-meter walk, 10-meter walk, and then that led to FDA approval. So we made this FDA approval now was done about a year ago with 4 to 5-year-olds, and you see the upper right panel. We have a phase 3 trial that in and of itself is 120 patients, but overall we've done over 200, and we expect approval for the entire Duchenne field by then. So I'm finished. You have excellent time. I was going to thank the team members, the participants in the trial, and some special people. Louise Rodino Claypack was my partner in this. She was a graduate, a postdoc, and now she's the head of Sarepta, which makes me very proud. And also Samuel Zaidi, who's here with me on this visit to Saudi, who was one of my fellows that helped build the success for SMA gene therapy. So I'll stop there and let either questions be asked or hear a highly informative lecture from Dr. Wang.
I think we'll take a few questions in this next few minutes. Are there any questions?
Fauzan Afraya from this institution, King Faisal. This was very inspiring. Thank you very much. You did mention gene replacement versus editing, and as you know, there is a lot of excitement these days about editing to replace genes. And I would love to hear your thoughts on inserting this through gene editing.
Well, gene editing has a major advantage of permanency. That's obvious. It has the limitation that I talked about in gene delivery. If it mistargets a place of gene replacement or mistargets the site of insertion, it can cause other diseases. And unfortunately, in the Duchenne world, the only patient that has so far received CRISPR met an unfortunate death. And so I think all those events kind of put things back. But I think that will be overcome, and I think the ultimate cure for this disease will be using gene insertion and gene editing.